Welcome to the Deep Dive, the show where we take the dense, often overwhelming technical foundation of a massive topic and distill it down to the essential architectural choices and surprising insights you need to master. Today, we are strapping in for a deep dive into UIKit.
UI.
The absolute bedrock, the very foundation of almost every successful native iOS application spanning back over a decade. It's huge.
That's right. And it's everywhere. When you look at an iPhone screen, everything you see, the smooth transitions, the dynamic layouts, the ability to scroll through thousands of data points without a stutter, that's UIKit at work. Our mission today isn't just to define the tools, it's really to cut through the complexity.
Right.
And clarify the fundamental trade-offs developers face every single day. We need to understand the implications of choosing, say, visual tools versus code, how application interfaces are structured, and the critical mechanics that ensure high performance, especially when dealing with massive data sets. That's key.
Our sources today are a brilliant, pragmatic developer's technical guide laying out the key decisions point by point. We're covering everything from the internal architecture that causes those dreaded storyboard XML merge conflicts to the mathematical foundation of auto layout and all the way to advanced performance tricks like the cell reuse mechanism. We're going to give you the shortcut, hopefully, to understanding the internal mechanics required to build a world-class application.
And this goes beyond mere syntax. This is about architectural longevity. It's not just knowing that, say, XIDs exist. It's understanding the performance and team collaboration benefits they unlock compared to, like, a monolithic storyboard. We're focusing on the foundational knowledge that prevents those silent, lurking bugs and performance bottlenecks that only show up 6 months into a growing project.
Okay, let's unpack this. We have to start at the absolute beginning, the UI decision matrix.
Right.
When you start a new screen, what is the trade-off inherent in the three major ways we define an interface? You've got storyboards, XIBs, and pure programmatic UI. Where do we start?
Well, that initial choice of how you define your UI, it really sets the tone for the entire development project, especially, I'd say, for large teams. Historically, the most popular starting point has been the storyboard.
Storyboards, right. The visual blueprint, often containing the definition of an entire app or maybe a major module. They are single, large visual files that contain multiple screens, multiple view controllers, and crucially, they visually show the entire application flow via those little arrows, the segues.
That visual representation of navigation is certainly the primary advantage. I mean, for quick prototyping, it's kind of unbeatable.
Yeah.
You drag and drop elements, you connect actions and outlets with control click, and the built-in interface builder handles the visual configuration of auto layout constraints. You see instant feedback, saving tons of boilerplate code compared to doing it manually in Swift.
That sounds fantastic, especially for maybe a junior developer or just rapid prototyping. But isn't it true that for many large teams, the moment you commit to a single monolithic storyboard, you are essentially signing up for, well, maintenance and collaboration hell down the road? We hit that scalability issue pretty fast, don't we?
You hit the nail right on the head. The primary, I'd almost say existential headache for teams using large storyboards is the dreaded merge conflict.
The merge conflict.
We have to remember what a storyboard truly is deep down. It's not some magical image file. It is fundamentally a massive XML file.
And XML is notoriously bad for merging. So when you have two developers, say Alice adds a button on screen A and Bob changes a constraint on screen B,
right,
and they both commit changes to the same XML file at the same time, Git just throws up its hands. It cannot figure out how to merge those changes seamlessly.
Precisely. And the complexity isn't just cosmetic, it's structural. When two developers edit the same view controller in Interface Builder, literally hundreds of lines of cryptic XML defining coordinate origins, specific constraint IDs, relationship tags like segue or view controller, they just get jumbled.
Yeah, it's a mess.
It often takes hours, sometimes days, to manually resolve these conflicts, carefully trying to piece together the intended UI logic without corrupting the file. That leads to massive friction and, honestly, decreased productivity. And that's not even mentioning that a large storyboard is also inherently slow to load and manage in Xcode itself.
And there's a performance overhead too, isn't there? Particularly at launch. Our source material notes that if a storyboard defines dozens of view controllers, the system might need to parse a significant portion of that XML into memory when the storyboard is first loaded, even if the user only lands on the initial screen. That adds to application launch time compared to loading simpler programmatic views.
That realization that storyboards are fantastic visually but kind of fragile structurally is why many established teams adopt the middle ground XIB files, often pronounced zib files.
XIBs. Right, so these are often defined as a visual file representing just a single self-contained UI component or maybe a single view controller screen. They're like modular pieces of the storyboard universe.
Exactly. The key scenario where you choose XIBs over storyboards is for component reusability and isolation. Imagine you need a complex custom table view cell, or a specific header, or maybe a custom overlay that needs to appear on 20 different screens.
Okay.
You define that once in XIB, and then you can dynamically instantiate in code wherever you need it. Storyboards. They struggle with that level of component modularity without requiring duplication or complex referencing.
So XIBs give us those really valuable visual design benefits of Interface Builder, but because they isolate components, they significantly reduce the chance of merge conflicts, since two developers are much less likely to edit the same single component XIB at the same time. And they make the overall project structure far more manageable. The trade-off, of course, is that you lose the overall visual map of the app's navigation flow. All navigation has to be wired up explicitly in code.
Which naturally leads us to the third option, programmatic UI.
Full code.
Full code. The entire interface, down to every button, every constraint, is created entirely using Swift code. No visual tools involved.
This is the developer's choice for absolute granular control, right? The pros seem obvious. Full control over every pixel, much easier maintenance in massive modular applications, and critically, zero merge conflicts in version control related to the UI definition, because the UI is just Swift code, which Git handles beautifully. It's easily diffable.
But the cost is paid upfront in time and boilerplate code. Visual prototyping is immensely slower.
Right.
You don't drag a view, you have to manually instantiate it, add it as a subview, and then you write lengthy code, whether using the older visual format language, VFL, or modern layout anchors, to define every single constraint. It takes, 10 lines of code to define a simple button centered on a screen that literally takes 10 seconds in Interface Builder.
So if we connect this to the bigger picture, the decision between these three methods, storyboards, XIBs, programmatic, it's a perpetual negotiation, isn't it? It's between speed of prototyping, which favors storyboards,
Right.
and the long-term maintainability, modularity, and team collaboration benefits you get from programmatic code, or perhaps those nicely split XIBs.
Absolutely. For a large organization, the time spent writing boilerplate code is often, in the long run, cheaper than the hours lost resolving horrible XML conflicts.
That makes sense.
That's why the common strategy to mitigate storyboard pain often involves either splitting massive storyboards into smaller, more focused ones, maybe one per feature flow, or isolating reusable components into XIBs. You're basically managing the surface area for team conflicts. It's about choosing your flavor of pain up front to prevent massive headaches later.
That's a brilliant way to frame that UI choice. Okay, so once we commit to a structure, visual, or programmatic, the next headache is ensuring the user can actually get around the app. That brings us to the choreography of the navigation stack. Moving through an app isn't just about flicking between static screens. It's this carefully orchestrated, stateful dance managed by the view controller lifecycle and the navigation stack. Let's start with the transitions themselves, the segues.
Right, a segue. It's fundamentally an object, and it defines the path and the transition style between two view controllers. It takes care of the animation and also the necessary data management that has to happen during that transition. The core built-in types are fundamental to understand. Push, which implies a hierarchy, like drilling down into details.
Like in a settings menu.
Exactly.
Yeah.
Then there's show, or show detail, common in iPad master detail layouts. Present modally, which typically covers the current screen temporarily for a task.
Like a login form.
Perfect example.
Yeah.
And popover, which you see a lot on iPad too. Plus, you can make custom ones.
Now, here's where the developer needs to get their hands dirty, especially with storyboards. If you are using a storyboard segue, you don't manually initialize the destination view controller. The segue object itself does it for you.
Correct.
This means the critical step for setting up the destination, especially passing required data, happens in a very specific method, right?
Absolutely correct. You can't rely on standard initializer injection like you might elsewhere. That's why the system specifically calls the prepare4.sender method in the source view controller, the one initiating the segue right before the transition animation begins. This is your mandatory contract with the segue system. Inside this method, you check the segway's unique identifier. You usually give them names in the storyboard. Then you faithfully cast the segue.destination property to the correct view controller type, and then you manually inject any data the next screen needs to load properly.
And if you miss that step, or maybe your data is nil when it shouldn't be,
Disaster.
the destination view controller loads without the necessary context, and the app either crashes or, maybe worse, shows inconsistent or bad state.
Yeah. So walking through the full life cycle of a segue. First, the segue object itself is instantiated by the system. Second, prepare for .sender is called in the source VC, enabling that crucial link and data transfer. Third, the transition performs its animation to push the modal slide up, whatever it is. And fourth, upon completion, the destination view controller takes over the control of the application state, becoming the active screen.
This controlled transfer leads us directly to the foundational structure for most hierarchical applications, the navigation stack.
The navigation stack. Yes, we're talking primarily about the UI navigation controller. It's a container view controller that manages a strict ordered array of view controllers based on the LIFO principle. Last in, first out.
LIFO, okay, so like a stack of physical pages.
Exactly like a stack of pages. The very first screen the user sees, the one you initialize the navigation controller with, is the root view controller. It sits immovably at the bottom of the stack.
Can't get rid of that one easily.
Right. Then, when you push a new screen, that new view controller is added to the top of the stack. The previous screen remains present in memory, just hidden beneath the new one.
Okay.
When you pop, the top view controller is removed, hopefully released from memory, and you automatically return to the screen that was just below it. The navigation controller conveniently handles the visual title bar and the back button functionality for you.
Understanding this structure is absolutely critical when we look at the difference between pushing a view controller versus presenting one modally. These aren't just aesthetic choices. They have drastically different memory implications, as you mentioned.
They really do. Push only works if you are already embedded within a UI navigation controller. That's the first constraint.
Got it.
The key memory characteristic is that when you push the previous view controllers, the entire history beneath the current screen on the stack remain in memory. They are still allocated.
So memory consumption goes linearly with the depth of the stack.
Pretty much, yes.
Yeah.
Those VCs are kept alive and active in memory until they are explicitly popped off.
Yeah.
This is perfectly suitable for deeply connected hierarchical flows like browsing categories, then products, then details. But a really big stack containing memory-heavy view controllers can definitely lead to a high memory footprint, potentially triggering warnings from the OS.
And in contrast, presenting a view controller modally, this creates a new screen that typically covers the current screen completely. Let's zoom in on the memory behavior here.
Okay, so when a modal view controller is dismissed, say the user taps done or cancel, it is intended to be released immediately from memory.
Intended being the key word. Exactly. It's ideal for temporary, often dead-end tasks like a quick settings change, composing an email, or that login prompt we mentioned. If everything is set up correctly, the memory is freed up immediately when it's dismissed.
What?
But this relies entirely on the developer ensuring there are no strong reference cycles keeping it alive. Things like strong delegate pointers pointing back, or complex closure captures, or any circular dependencies. These can prevent the presented VC from being deallocated even after dismissal.
Ah, the dreaded retain cycle.
Precisely. If you fail to break those cycles or null out those references, the presented VC lingers in memory, invisible to the user but still consuming resources. It creates a silent memory leak that degrades app performance over time.
So, if your app is getting sluggish and you notice memory usage creeping up and up, you should look really hard at your deep navigation push stacks. Maybe see if some intermediate controllers can be removed programmatically.
Good point.
And scrutinize any modal presentations that don't seem to trigger a clean DNet log when they're dismissed. That DNet log is your friend. It absolutely is, which leads perfectly into the view controller lifecycle itself. These methods are precisely where you manage your memory, your data fetching, your UI updates, and your overall performance.
Okay, the lifecycle methods. The journey starts with init, the controller is created, then potentially load view. When would you use that?
Load view is specifically for when you are building the entire view hierarchy programmatically without a storyboard or XIB. You override load view to create the main view property of the controller and add your initial subviews. If you use Interface Builder, you generally don't touch this.
Got it. Then we hit the famous one, view did load.
Yes, view did load. Our sources stress this, and it's crucial. It is called only once per view controller instance, right after the view hierarchy has been successfully loaded into memory from the storyboard, XIB, or your load view method, only once. This makes it the safe, optimal place for one-time initialization tasks. Setting up static UI elements that don't change, fetching necessary data that won't change frequently during the screen's lifetime, initializing variables, adding gesture recognizers, things you only need to do upon creation.
What's the implication of misusing view did load? Say I put something that needs to update every time the screen appears in there.
Well, it just won't update. If you put, say, code to refresh the UI based on some external state in view did load, it will only run the first time. When the user navigates away and comes back, that code won't run again and they'll see stale data.
Okay.
More critically, the performance issue can arise if developers confuse view did load with the appearance methods. View will appear or view did appear.
Right. The appearance methods are distinct because they are called every single time the view is about to appear on screen or has just finished appearing.
Exactly. Every time. So you should never put a heavy, potentially long-running, uncancelable network call directly in view will appear unless you absolutely have to and have thought about cancellation. Because if the user rapidly pushes and pops back and forth,
That call gets fired repeatedly.
potentially causing UI flicker if it updates the screen, or just massive battery drain and network usage in the background. View will appear is much better suited for things like refreshing time-sensitive UI elements like a clock, restarting animations that were paused, or setting up delegates or observers that only need to be active when the view is actually visible.
And correspondingly, view will disappear and view did disappear are where you must remember to clean up.
Absolutely. Stop timers, invalidate observers, cancel any ongoing network requests started in view will appear, save temporary user input or state. Basically, reverse whatever setup you did in the appearance methods to prevent leaks and unnecessary background activity.
And finally, if everything goes right and all strong references are broken,
DNIT is called. This is the view controller's deinitializer. Seeing your log message here is your final confirmation that the controller object has been successfully deallocated and its memory reclaimed by the system. If you don't see DNIT being called when you expect it, like after popping or dismissing, you likely have a retain cycle somewhere.
that distinction, once only set up in view did load versus recurring setup teardown in the appear disappear methods, is absolutely key to managing resources effectively. Okay, let's wrap up this section on flow by looking quickly at adaptive presentation and deep linking.
Right, adaptive presentation. This is what really allows us to write once, run everywhere, or at least closer to that ideal. iOS uses something called trait collections, specifically horizontal and vertical size classes. You get compact or regular for each dimension.
Like on an iPhone versus an iPad.
Exactly. Or even split screen. Multitasking on an iPad changes these. The system automatically adjusts the UI presentation based on these traits. For instance, a modal presentation that takes up the whole screen on a compact width environment, like an iPhone in portrait, might automatically render as a centered, smaller form sheet in a regular width environment, like an iPad, without you writing specific code for each case. You rely on the system to decide the best presentation style, making your UI code more device agnostic.
Very cool. And what about deep linking? If I send a user an email with a link like myapp.profile123, how does the app, which might be closed or in the background, know how to open directly to that specific user's profile screen?
It's a multi-stage architectural challenge, really. It's not trivial. First, the app delegate, or in modern apps, the scene delegate, must be configured to receive and parse that incoming URL. This involves identifying your custom scheme, my app in your example, and extracting the path components and any parameters, like profile and the ID 123.
Okay, step 1, parse the URL.
Step 2, the application logic needs to figure out where that screen actually lives in the potential navigation hierarchy. Is profile something pushed onto the main tab's navigation controller, or presented modally?
Right, map the URL to a destination.
Step 3, you must programmatically navigate the UI navigation controller stack, or whatever structure you have, to get there. This often means ensuring the root view controller is set correctly, maybe switching tabs if needed, and then performing the necessary sequence of pushes or presentations to build the required view hierarchy and land the user directly on that target screen, often passing the parsed data, like the profile ID, along the way using prepare for .sender or other means if navigating programmatically.
That sounds complex, especially if the app wasn't running. You might have to completely reconstruct the navigation state.
It is complex. You have to handle cases where the user needs to be logged in first, or where intermediate data needs to be loaded. Deep linking requires careful planning of your app's navigation structure and state management.
That's a huge shift from simply displaying fixed screens to managing this dynamic, stateful stack that can be entered from multiple points. Okay, now let's talk about ensuring those screens look right everywhere, regardless of orientation, device size, or even the user's preferred text size. Time for auto layout.
Yes, auto layout. We absolutely must tackle this. It was one of the biggest paradigm shifts in iOS development history, moving developers away from manual positioning to using declarative rules.
Before auto layout, which arrived around iOS 6, developers used fixed frames, setting the exact X, Y, width, and height in points, and maybe some manual resizing masks, the old springs and struts system. And we all remember how brittle that was.
Oh, it was a nightmare.
Yeah.
Fixed coordinates worked okay for maybe the original iPhone screen size, but the moment you rotated the device, or Apple introduced the taller 4-inch iPhone 5, or later the dramatically wider plus-size models, or iPads, the layouts just failed catastrophically. Views would overlap, run off screen, or leave huge gaps.
Yeah, you'd end up writing tons of messy Eiffels code just to manually recalculate every single frame on rotation or for different devices. It was not maintainable.
Auto layout solved this by fundamentally changing the approach. Instead of telling a view exactly where to sit using fixed coordinates, x10, y10, width 100, height 50, you define relationships or rules between UI elements.
So instead of coordinates, it's like saying this button's leading edge should be 8 points from the superview's leading edge, or this label should be centered horizontally in its container, or these two buttons should have the same width.
Precisely. You define these relationships using constraints. The genius of the system is the underlying algorithm that takes potentially hundreds of these rules for a complex screen and solves them simultaneously, like a system of linear equations and inequalities.
And that underlying engine is something called the cassowary algorithm, right? That's the deep architectural detail.
That's right. Cassowary is a highly efficient incremental constraint-solving algorithm. It's designed specifically to solve these systems of linear equations and inequalities, like view A.leading plus 8 equals view B trailing. At runtime, when the layout needs to be calculated, iOS feeds all the active constraints for a view hierarchy into this solver.
And it figures out the math.
It mathematically calculates the precise X, Y, width, and height, the final frame for every single view that satisfies all the required constraints and, as optimally as possible, satisfies any optional constraints based on their priorities. It finds a unique solution if the constraints are set up correctly.
That's the real magic. It's not a guessing game or approximation. It's mathematical certainty based on the rules we define. We define the relationships. Positional ones like leading, trailing, top, bottom, center X, center Y.
Size constraints like width and height or aspect ratio.
And relative constraints like the spacing between elements.
But the real mastery, where auto layout truly shines, comes when we factor in dynamic content. This is where content-driven layout takes over. Think about a UI label. If it's displaying a short name like OK, it needs less space than if it's displaying a long paragraph of text.
Right, the size changes based on the content.
Auto layout uses the concept of intrinsic content size. This is the natural optimal size the UI element, like a label or a button, needs to display its current content without being truncated or having unnecessary empty space around it.
Okay, intrinsic size. And auto layout uses two critical properties to decide how a view should behave relative to that intrinsic size, especially when space is limited or plentiful. These are content hugging and compression resistance. They sound kind of similar.
They do, but they control opposite forces. Content-hugging priority defines how strongly a view resists growing larger than its intrinsic content size. Think of it as hugging its content tightly.
So high hugging means don't stretch me.
Exactly. If you have two labels side by side, and you want one label, say a short title, to stay at its natural width, while the other label, a longer description, should stretch to fill the remaining space, you give the short title label a higher horizontal content-hugging priority. The layout system will satisfy that higher priority, keeping it snug, and force the other label to grow.
Okay, hugging prevents unwanted growth. What about compression resistance?
Compression resistance priority is the opposite. It defines how strongly a view resists shrinking smaller than its intrinsic content size. Think of it as resisting being squished.
So high resistance means don't shrink me.
Precisely. If space gets tight, and you have two labels again, the label with the lower compression resistance priority will be the first one to get truncated, maybe showing. You give important text, like a price or a critical warning, a higher compression resistance priority to ensure it remains fully visible, even if other elements have to shrink.
This leads directly to the mechanism for resolving potential conflicts and constraints. Constraint priorities. If the cassowary solver finds a contradiction, like two rules pulling a view in opposite directions, how does it decide which rule to break or ignore?
Every single constraint you create is assigned a priority, a number ranging from 1, the lowest, barely a suggestion, up to 1,000, which means required.
1,000 is required, must be satisfied.
Must be satisfied. If the solver encounters 2 or more required priority 1,000 constraints that directly contradict each other, say one constraint forces the width to be exactly 200 points and another forces the same width to be exactly 300 points, you get an unsatisfiable constraint error at runtime, usually with a log message. The layout is broken.
So you can't have contradictory required constraints. How do you handle situations where you have a preference, but it's not absolutely mandatory?
That's where priorities less than 1,000 come in. This is often the expert move. Instead of making everything 1,000, you might set a critical constraint to 1,000, like stay within the screen bounds, and a competing less critical constraint, like try to be 300 points wide, to a slightly lower priority, maybe 999 or 750, which is often used for high priority.
Why 999? That seems really close to 1,000.
Setting it to 999 signals a very strong preference. It allows the constraint to be satisfied in almost all situations, but it provides the solver with an escape hatch. It tells the solver, try really, really hard to meet this 999 constraint. But if you absolutely cannot satisfy it without violating 1,000 priority constraint, then you have my permission to break this 999 one first. It's a form of declarative finesse that helps avoid both the ambiguous layout errors, where there isn't enough information to determine a unique layout, and the unsatisfiable constraint errors, where there's too much contradictory required information. You guide the solver.
That makes sense. Beyond conflicts between our own constraints, we also have to respect the geometry of modern devices, especially iPhones with notches or home indicators. This means using the safe area.
The safe area is absolutely critical for modern iOS development. It was introduced with the iPhone X. It defines the usable canvas area of the screen, the portion where your content is guaranteed to be safe from being obscured by system UI elements, like the status bar at the top, the navigation bar if present, the tab bar at the bottom, or the home indicator swipe area on newer phones without a physical home button. It also accounts for device notches and rounded corners.
So instead of pinning constraints to the absolute edge of the superview, we should generally pin them to the safe area layout guide.
Generally, yes. By constraining your primary content views to the edges of the safe area layout guide, your layout automatically adapts to these different intrusions, ensuring a consistent and usable experience regardless of the specific device shape or orientation. Backgrounds or decorative elements might still go edge to edge, but interactive content should respect the safe area.
Now, let's briefly introduce a core architectural concept here that ties into how views are drawn, something we'll touch on again later. It's the separation between the structural layout handled by UI view and the actual rendering, which is handled by its underlying K-layer.
Yes, this is a key deep dive nugget. Every UI view you work with, every button, label, image view, container view, has an underlying K-layer, which comes from the core animation framework. The UI view class acts as a wrapper around this layer.
So what does the UI view do versus the K-layer?
Broadly speaking, the UI view is responsible for handling user interaction, touches, gestures, managing the view hierarchy, adding subviews, and crucially, participating in the auto layout system, defining and solving constraints. The K-layer, on the other hand, is responsible for the actual visual rendering and drawing of the view's content onto the screen. It handles things like the background color, borders, shadows, corner radii, opacity, and efficiently managing animations of these visual properties.
This distinction is why you sometimes see properties that seem to do similar things, but one belongs to the UI view and one belongs to the K-layer, like clips to bounds on the view and masks to bow on the layer.
Exactly. Clips to bounds is a UI view property. Setting it to true instructs the view itself to clip any subviews that extend beyond its calculated bounds during the layout phase. Masks to bounds is a K-layer property that does essentially the same thing, but at the rendering level for the layer's content and its sublayers.
So why have both?
Often, they behave identically, and setting one might set the other, but the separation matters in subtle cases. For example, if you want a shadow effect, which is drawn by the K-layer that needs to extend outside the view's actual frame, you typically need clips to bounds on the UI view to be false. But then you might need to manipulate the K-layer's shadow properties directly. Understanding this architectural separation, that the view handles layout and interaction, while the layer handles drawing and animation, is key to solving tricky visual bugs and implementing advanced effects.
That sets the stage perfectly for the final part of auto layout we need to cover: how and when these layout calculations actually happen. This involves the layout cycle methods.
Understanding the timing of the layout cycle is crucial for debugging flickering UI and ensuring smooth animations. If you make a programmatic change that affects a view's layout, like changing a constraint's constant value, activating, deactivating constraints, or sometimes even changing the text in a label which changes its intrinsic size, you need to tell the system that the layout is now invalid. You do this by calling setNeedsLayout on the affected view or one of his ancestors.
Okay, so setNeedsLayout is like raising a flag. Hey, something changed. My layout might be wrong now.
Exactly. It's like marking my room as dirty, as the analogy goes. It tells UIKit that a layout recalculation is necessary for this view and its subtree, but crucially, it happens asynchronously. UIKit usually waits until the next update cycle of the run loop to actually perform the layout pass, potentially batching multiple layout requests together for efficiency. It doesn't happen immediately when you call the method.
So it marks it as needing an update later. What if I need the layout to be updated right now? For example, before starting an animation.
That's where layout comes in.
Yeah.
This is the synchronous counterpart. Following the analogy, it's like saying, I need to clean my room right now.
Force the layout pass.
It forces an immediate synchronous layout pass for the receiver view and its subtree, but only if that view has already been marked as needing layout by a previous call to setNeedsLayout. If the layout isn't marked as dirty, calling layOfNeeded does nothing.
Ah, okay. So you usually call setNeedsLayout first, then layOfNeeded.
Often, yes. A common pattern for animations is make your constraint changes, call setNeedsLayout on the parent view, then immediately call layOfNeeded inside an animation block. This forces the system to calculate the final layout positions before the animation starts, allowing it to animate smoothly from the old state to the new state.
And the last piece of this puzzle is layout subviews. When does that get called?
Layout subviews is the method where the actual layout work happens. It's like the actual cleaning process. This method is called automatically by UIKit during the layout pass that was triggered either automatically by the system or manually via layoutNeeded. Its default implementation uses the constraints solved by the auto layout engine to calculate and set the final frame for each subview.
So we usually don't call layout subviews directly.
Correct. You almost never call it directly. You would override layout subviews within a custom UI view subclass only if you need to perform some custom non-constraint-based layout logic. For example, if you need to manually position or size some subviews based on complex calculations that auto layout can't handle easily, even then, you should always call super.layout subviews within your override, usually first, to let auto layout do its work before you make your custom adjustments.
Okay, so the flow is change constraints, change some layout.
Mark says dirty async.
Update
Update cycle happens.
Update
layout subviews is called automatically keyframes are set. That's the essence of it. setNeedsLayout queues the work, layos if needed, executes it synchronously if needed, and layout subviews does the actual positioning. Misunderstanding this timing can definitely lead to janky animations, visual glitches, and frustrating debugging sessions.
All right, moving beyond static responsive views, we now tackle arguably the largest performance hurdle in almost every iOS app, displaying massive amounts of data efficiently. Whether it's 100 emails, 1,000 photos, or 10,000 chat messages, you simply cannot build 10,000 distinct UI views at once without grinding the app to a halt.
Absolutely not. That would be disastrous for performance and memory. This is where the workhorses of dynamic data display come in. UItable view and UI collection view.
Let's start with the differences. UItable view is the older, perhaps simpler one.
Yes, UItable view is the foundational choice for displaying data in a single column list, scrolling vertically. It's highly optimized for structured, relatively uniform data. Think settings, screens, contact lists, email inboxes, basic chat interfaces. It supports sections, headers, and footers easily.
And UI collection view, what does it offer beyond the table view?
UI collection view is the vastly more flexible and powerful tool. While it can replicate a simple vertical list like UItable view, its real strength lies in supporting complex layouts. Think multi-column grids like a photo gallery, tiled layouts, horizontally scrolling carousels, even completely custom dynamic layouts where items might have different sizes or positions. It's built on a more abstract and extensible layout system. If you need anything beyond a straightforward single-column vertical list, you generally jump to UI collection view.
Okay. Different layout capabilities, but underneath, when it comes to handling potentially thousands or millions of items without crashing, they rely on the same core performance optimization trick, right?
They do. Regardless of their presentation stylist or grid or custom, their high performance relies entirely on the same fundamental mechanism. Cell reuse. This is probably the single most important concept to understand for efficient iOS data display.
Cell reuse. Why is it so vital? Let's break down the problem it solves.
The performance sinkhole, as you hinted, is object allocation and memory consumption. If you have a list with, say, 10,000 items, and you were to naively create 10,000 UItable view cell or UI collection view cell objects, which are subclasses of UI view, the app's memory footprint would spike instantly.
Yeah, 10,000 views, each potentially with subviews like labels and images.
Exactly. The CPU would struggle to manage rendering and layout for that many active view objects simultaneously. Scrolling would become incredibly jerky, and the app would likely become unresponsive or simply crash due to excessive memory pressure. It just doesn't scale.
So how does cell reuse solve this scaling nightmare?
Cell reuse solves this by adhering to a simple but brilliant principle. Only keep enough cell objects in memory to display the currently visible rows or items, plus maybe a small buffer of cells just above and below the visible screen area to prepare for scrolling.
Okay, so maybe only 10 or 20 cells are actually allocated at any given time, even if the data source has thousands of items.
Precisely. As a cell scrolls off the screen, it is not destroyed. Instead, it's essentially stripped of its current data content and placed into a reuse pool, or a cache, which is managed internally by the table view or collection view. Each cell in this pool is identified by a unique string, the reuse identifier.
The reuse identifier, you set this when you create or register the cell type.
Correct. So when the user scrolls down, and the system needs to display a new cell for, say, row 100, it doesn't allocate a brand new cell object from scratch. Instead, it asks the reuse pool, do you have an unused cell with the identifier, my custom cell identifier?
And if the pool has one that just scrolled off screen at, say, row 10?
If the pool has a matching cell available, the table collection view dequeues it from the pool. This dequeued cell is essentially an old recycled cell. The system then hands this recycled cell back to your data source code, specifically the cell for row at or cell for item at method. Your code is then responsible for configuring this dequeued cell with the new data for row 100, and then the system puts it back on screen.
So the internal recycling process is scroll off, enter reuse pool, scroll on dequeue from pool configure with new data display.
That's the core loop. It's incredibly efficient because you avoid the expensive process of allocating new view objects and deallocating old ones constantly during scrolling. You're just quickly reconfiguring a small set of existing cell objects. The table collection view maintains that reuse pool, which is usually implemented as a dictionary or similar structure, keyed by the reuse identifier.
Okay, dequeue reusable cell with identifier.4 is the key matted call here. What happens if the pool doesn't have a cell with the right identifier, maybe at the very beginning when the screen first loads?
Good question. If dequeue reusable cell looks in the pool and doesn't find an available cell with the requested identifier, which typically only happens for the first few cells needed to initially fill the screen, then and only then will it automatically allocate a new cell instance based on how you registered it, either from a storyboard prototype, a XIB file, or a class. This newly created cell is then returned, configured, displayed, and eventually when it scrolls off, it gets added to the reuse pool for later recycling.
We talked about configuration errors earlier in the context of segues. It sounds like configuration is absolutely critical here too. If you're getting back an old cell that used to display data for row 10, and now you need it for row 100.
This is where the infamous table view collection view data leakage bug comes in. It's the classic beginner mistake, and even experienced devs slip up sometimes.
How does it happen?
Because you're reusing an existing object, that object might still hold visual state from its previous use. For example, suppose for row 10, you set the cell's background color to light gray because it was marked as red. Now you dequeue that same cell for row 100, which should be unread and have a white background. If your configuration code for row 100 only sets the text labels but forgets to explicitly reset the background color back to white,
the cell will still have the light gray background from row 10.
Exactly. The user sees stale state from a completely different data item. The cardinal rule of cell reuse is, in your cell for row at cell for item at method, you must treat the dequeued cell as a completely blank slate. You must explicitly configure every single visual and functional property based on the data for the current row or item index path. Assume nothing about the cell's previous state. Always set the text, the image, the colors, the accessory view type, everything, every single time.
Reset everything, don't rely on defaults carrying over.
Precisely. That need for meticulous manual management of cell state, combined with the complexity of manually telling the table collection view exactly how the UI should change when the underlying data changes. Insert this row, delete that row, move this section, led Apple to introduce a more modern architectural evolution. The diffable data source, starting in iOS 13.
Diffable data source. Okay, what problem does that solve compared to the traditional data source protocols?
Traditionally, if your underlying data array changed, say you fetched new items, the user deleted an item, or items were reordered, you had to manually inform the table or collection view about these changes. You'd call methods like insert browse at delete rows and move row at datio, or maybe reload sections.
And sometimes in desperation, or if the changes were too complex, you just call reload data.
Right. And reload data is terrible for performance and user experience. It forces the entire visible view hierarchy to be thrown away and recreated from scratch, often causing a noticeable visual flash or jump, losing scroll position, and doing way more work than necessary.
And the manual methods like insert rows, those were error-prone.
Extremely error-prone. You had to perform the data model update, e.g. remove item from array, and then inside a perform batch updates block, call the corresponding UI update methods delete rows with the exact index paths that match the state before the data model change. If your data model update and your UI update calls got out of sync, even slightly.
Crash. And its internal inconsistency exception.
The dreaded crash. It was a constant source of bugs, especially with complex updates or asynchronous data loading. Diffable data source completely abstract away this fragile synchronization complexity.
How does it work? What's the core idea?
Instead of imperatively telling the UI how to change, insert here, delete there, you work declaratively. You simply create a snapshot object and a diffable data source snapshot that represents the desired final state of your UI, which sections exist, and which unique item identifiers belong in each section in the correct order.
So you just describe what the screen should look like now.
Exactly. You build this snapshot representing the new state, and then you apply the snapshot to the diffable data source. That's it.
And the system figures out the rest.
The system takes over. It uses a highly efficient hashing and diffing algorithm internally to compare the new snapshot you just applied with the previous snapshot it was displaying. It automatically calculates the minimal set of differences, the delta between the two states.
So it figures out which items were added, removed, moved, or maybe just reloaded.
Precisely. And then critically, it automatically performs only those necessary fine-grained UI updates. Insert rows, delete rows, move a row, etc. on the underlying table or collection view, often with smooth default animations.
Wow. So it eliminates the need for manual index path calculations and the risk of inconsistency crashes.
Completely. And the performance improvement is often massive compared to calling reload data. Because it only updates what actually changed, it significantly reduces the computational load and avoids unnecessary rendering work. It's a fundamental shift toward declarative UI management for list and grid data, making code cleaner, safer, and often faster.
That transition from manual imperative updates, do this, then do that, to declarative snapshot-based updates, this is the state I want, seems to be a core theme across a lot of modern UI frameworks, not just in iOS. Okay, so we can display data efficiently. Now let's move from displaying data to actually receiving input from the user.
Right. The next crucial part of the architecture is handling user input effectively. Beyond simple button taps, which are typically handled directly by the straightforward target action pattern, button.add target, more complex interactions usually require using UI gesture recognizer.
Gesture recognizers. So these are objects that encapsulate the logic for interpreting raw touch data into meaningful gestures.
Exactly. They provide a huge abstraction layer. Instead of you having to write complex mathematical code to track touch locations and timing, to figure out if a sequence of touch movements constitutes, say, a mingle tap, a double tap, a drag pan, or a two-finger pinch or rotation, the built-in gesture recognizers handle all that low-level interpretation for you.
You just create an instance of the recognizer, attach it to a UI view, and give it a target and action method to call when the gesture is recognized.
Pretty much. And iOS provides a standard set of built-in types covering the most common interactions. UI tap gesture recognizer, UI long press gesture recognizer, UI pin gesture recognizer for continuous dragging, UI pinch gesture recognizer for zooming, UI rotation gesture recognizer, UI swipe gesture recognizer for directional swipes, and UI screen edge pan gesture recognizer for swipes starting near the screen edge. often used for navigation.
When we implement a gesture, the simple approach is target action, like with buttons. It calls a single method directly when the gesture's state changes, usually when it's recognized. But for more complex situations, like maybe I want a pan gesture and a pinch gesture on the same view to work simultaneously, I probably need to use the delegate pattern, right?
Yes, the UI Gesture Recognizer Delegate Protocol gives you much finer-grained control over the gesture recognition process. Target action is great for simple, one-off gestures, but the delegate methods allow you to intervene at key points. For example, there are delegate methods that let you decide whether a gesture recognizer should even begin trying to recognize a gesture based on the initial touch, or whether it should receive a particular touch event at all. And crucially, there are methods like gesture recognizer should recognize simultaneously with that allow you to explicitly permit two or more different gesture recognizers attached to the same or related views to recognize their gestures concurrently.
So that's how you could implement pinch to zoom while simultaneously panning an image. You'd return true from that delegate method for the pinch and pan recognizers.
Exactly. Without the delegate allowing simultaneous recognition, typically once one gesture recognizer successfully claims the touch sequence, it prevents others from recognizing. The delegate gives you the power to override that default behavior and orchestrate more complex, combined interactions.
Okay, so gestures abstract the raw touches. But what happens even underneath the gesture recognizer? When a user physically touches the screen, how does the system figure out which specific view, potentially nested 5 layers deep inside other views, is the intended recipient of that initial touch event? This is governed by something called the responder chain, isn't it?
That's right. The responder chain is the formal structured hierarchy of objects. UI responder subclasses, which include UI view controller, UI window, UI application, and UI application delegate, that have the ability to respond to various types of events, including touch events, motion events like shaking the device, remote control events, and even keyboard presses on external keyboards.
So it's not just a random broadcast, it's an ordered path that events follow.
It's a very specific path. When a physical touch occurs on the screen, the system hardware detects it, and UIKit creates a UI touch object representing that finger contact, bundling it inside a UI event object. The first thing the system does is perform what's called a hit test.
Hit testing, what's that?
Hit testing is the process of determining which UI view in the entire visible view hierarchy should be the initial target for that touch event. It works by starting at the UI window level and recursively checking down the view hierarchy using the hittest with method on each view. Essentially, it asks each view, does this touch point fall within your bounds? And if so, does it fall within the bounds of any of your subviews? It drills down until it finds the deepest, frontmost view in the hierarchy that contains the touch point.
Okay, so it finds the leaf node view under the user's finger. That view becomes the primary candidate to handle the touch.
Correct. That deepest view is the hit test view. The UI event containing the UI touch is then sent first to this hit test view.
And what happens then? Does it just handle it?
It can handle it. If that view has a gesture recognizer attached that recognizes the touch sequence, the gesture recognizer typically consumes the event. Or, if the view itself overrides the low-level touch handling methods, touches began, touches moved, touches ended, touches canceled, it can directly process the raw touch data. If the hit test view does handle the event, the process usually stops there.
But what if that deepest view doesn't handle it? Maybe it's just a simple background view, or it specifically chooses not to respond.
Then the event starts bubbling up the responder chain. If the hit test view doesn't handle it, the event is passed to its immediate superview. If the superview doesn't handle it, it goes to its superview and so on, up the view hierarchy.
So it travels upwards?
Yes. If it reaches the top-level view managed by a view controller without being handled, it's then passed to the UI view controller itself. If the view controller doesn't handle it, it continues up to the UI window, then to the UI application singleton object, and finally, if still unhandled, it might reach the app delegate. The event travels up this predefined chain until some object explicitly handles it or it reaches the end of the chain and is discarded.
That structure seems really useful. It allows higher-level objects, like a view controller or a container view, to potentially intercept and handle events that occurred on their child views, without needing direct references or complex delegation between them.
Exactly. It provides a clean mechanism for organizing event handling logic across complex view hierarchies. It also explains how things like system-wide gestures or handling keyboard shortcuts can work. They might be handled higher up the chain by the window or application object.
And what about multi-touch? How does the system handle tracking multiple fingers simultaneously, like for pinching or complex custom drawing?
Those same low-level touch handling methods, touches began, touches moved, touches ended, touches canceled, are designed for multi-touch from the ground up. The UI event object they receive contains a set of all UI touch objects currently associated with that event sequence. For example, all fingers currently down. Your code within these methods can iterate through the set of touches, track their individual phases, began, moved, ended, and locations using properties on the UI touch objects, allowing you to implement sophisticated multi-finger interactions if needed, although often using UI gesture recognizer is much easier.
Okay, shifting gears significantly now, but equally important for a good app. Ensuring that all users, including those with disabilities, can effectively use the interface. We need to discuss accessibility. This isn't just a nice-to-have or purely a regulatory compliance issue anymore, is it?
Absolutely not. Building accessible apps is fundamentally about good design and reaching the widest possible audience. It not only expands your potential market and ensures legal compliance in many regions, but it often makes the app better and more usable for everyone, not just users relying on assistive technologies. Things like supporting dynamic type, allowing users to change font sizes, improves readability for many users, not just those with low vision. Making sure your app works well with VoiceOver, the built-in screen reader, forces you to think clearly about your UI structure and labeling.
So what are the key technical things developers need to do to make their UIKit apps accessible? It often involves setting specific properties on UI elements.
Yes, the UI Accessibility Protocol and related APIs provide the tools. The three most critical properties you need to set correctly on your UI elements, UI views, UI controls, etc., are the accessibility label, hint, and value. Let's detail the subtle but important differences between them.
Okay, first, the accessibility label.
The accessibility label is the cornerstone. It must be a short, clear, localized string that concisely identifies the UI element. It's usually the first thing VoiceOver reads when the user focuses on the element. For a standard button, the label might just be the button's visible text, like save or cancel. For an icon-only button, like a trash can icon, the label must be set explicitly to something descriptive, like delete or trash. It should identify what the element is.
Okay, short, identifies the element. Second, the accessibility hint.
The accessibility hint provides brief additional information about what will happen when the user interacts with the element. It explains the action or result. VoiceOver reads the hint after a short pause, only if the user keeps focus on the element. So if the label for our trash button is delete, the hint might be double tap to permanently remove this item. Or for a setting switch label Wi-Fi, the hint could be double tap to toggle Wi-Fi connection. It clarifies the consequence of interacting.
So label is what it is, hint is what it does. And third, the accessibility value.
The accessibility value describes the element's current state or value, especially for controls that change. For a UIS slider, the label might be volume, but the value would be dynamically updated to read something like 50%. For UI stepper controlling quantity, the value might be 3 items. For a text field, the value is the text currently entered. If you have a custom control, like a star rating widget, you're responsible for updating the accessibility value. You give away 4 out of 5 stars whenever the user changes the rating, so VoiceOver users know the current state.
So label, hint, and value provide the core semantic information. What about announcing changes that happen dynamically on screen, like an error message appearing or content loading?
That's where accessibility notifications come in. If something significant changes on screen that isn't directly tied to the element the user currently has focused, VoiceOver won't know about it unless you explicitly tell it. You use UIAccessibility.post, notification.argument, to send notifications. For example, after submitting a form, you might post an announcement notification with the message, "Form submitted successfully." Or if navigating to a new screen programmatically, you might post a screen change notification to make VoiceOver announce the new screen title. These are crucial for keeping users of assistive technologies informed about dynamic UI updates.
Making sure those notifications are timely and informative is key. Okay, finally, let's go right back to the very, very beginning. The silent core that initiates this entire magnificent, complex system we've been discussing. The entire iOS application process begins with one single, somewhat hidden function call, right?
That's correct. Deep down, the initial entry point for almost every iOS application launched by the operating system is a C function called UI application main. You typically don't call it directly yourself anymore, especially with Swift projects using the app main attribute on the app delegate or app struct, but it's what's happening under the hood.
And what does UI application main actually do?
It performs the crucial bootstrapping tasks, to get the application off the ground. Its primary responsibilities include creating the singleton UI application object, which is the central hub managing the application's event loop and overall coordination, creating the application's delegate object, your app delegate, or in SwiftUI apps, the object conforming to the app protocol, and setting it as the delegate for the UI application instance. Initializing the app's main run loop, which is responsible for receiving and dispatching events like touches and timers, and setting up the initial user interface environment, typically by loading the main storyboard or instantiating the initial view controllers and connecting them to the UI window. Essentially, it acts as the gatekeeper, kicking off the entire application lifecycle, that endless cycle of receiving events, processing application logic, and rendering UI updates that defines every moment the app is running.
It truly is the silent workhorse that starts the whole complex machine we've just spent all this time unpacking. Amazing how much relies on that initial setup. Hashtag tag outro.
We've definitely covered a vast architectural spectrum today. It's quite a journey, tracing the structure all the way from defining an individual UI component right up to the application's launch process itself. We started by dissecting that crucial upfront architectural choice, the trade-off between visual tools like storyboards with their rapid prototyping advantages, but inherent scalability pain, especially those XML merge conflicts.
Yes.
Versus the long-term maintainability and team friendliness offered by more modular approaches, like using isolated XIBs for reusable components or going fully programmatic with Swift code.
Then we navigated through the strict, often memory-intensive rules of the LIFO navigation stack, really digging into the difference between the hierarchical push behavior, where previous screens linger in memory, and the more temporary, potentially immediately dismissible nature of presenting view controllers modally, highlighting those potential memory leaks if you're not careful with retain cycles.
We then tried to conquer the complexity of auto layout, moving conceptually beyond fixed coordinates to defining declarative mathematical relationships between views. Understanding that the cassowary algorithm is solving these constraints like equations is key.
And we saw how constraint priorities, along with content hugging and compression resistance, give developers the tools to declaratively manage layouts that adapt beautifully to dynamic content and varying screen sizes.
And finally, we looked at how high performance is achieved in data-heavy applications like tables and collections. It's not by brute force creating thousands of views, but by the clever, efficient recycling mechanism of the cell reuse pool.
Right, only keeping visible cells in memory. And how that whole process is made even safer and more efficient with the modern declarative approach of the diffable data source, letting the system handle the complex diffing and animation automatically.
Understanding these fundamental building blocks, really grasping the why behind things like the fragility of storyboard XML, the LIFO nature of the navigation stack, the mathematics of auto layout, or the computational efficiency of the reuse pool. That understanding is the only true shortcut to effectively diagnosing pretty much every major performance bottleneck or UI flow issue you will ever encounter in a UIKit-based iOS app.
So what does this all mean?
It means that every visual element you see on screen, every button, every label, every complex custom view, relies on a critical, often hidden architectural partnership. We touched on this earlier, the fundamental separation between the UI view object and its underlying drawing mechanism, the K layer from core animation.
Right, the view handles interaction and layout math, the layer handles the actual pixels, the rendering.
Exactly. And this separation isn't just academic. It has real-world consequences for how you build and debug your UI. So here's something to really chew on. Consider how that separation affects seemingly simple visual properties. Imagine you have a view, and you set clips to bounds true on the UI view itself.
Okay, so any subviews extending outside its bounds get clipped. Standard stuff.
Right. But now, let's say you also want to add a drop shadow to that same view. Shadows, visually, need to extend outside the view's calculated frame to be visible. But because the UI view's clips to bounds property is set to true, the view's rendering process respects that boundary.
So the shadow itself gets clipped along with the subviews. You won't see it.
Precisely. The shadow, which is drawn by the underlying K layer, gets clipped by the UI view's clipping instruction. To get the shadow to appear correctly while still perhaps clipping internal subviews, you often have to dive deeper. You might need to leave clips to bounds as false on the view, but then maybe manipulate the key layer's mask to bounds property, Or potentially restructure your view hierarchy, maybe putting the content needing clipping inside a subview that does clip, while the outer view with the shadow does not.
So the difference between setting a property on the UI view versus setting a seemingly similar property directly on its K layer can fundamentally change how visual effects like shadows or even corner radii interact with the view's content and bounds.
Exactly. It highlights that silent but absolutely critical relationship and division of responsibility between the view and its layer. It's a reminder that to truly master UIKit, you can't just operate at the surface level of UI view. You always need to be aware of, and sometimes directly manipulate, the powerful core animation layer lurking just underneath. It's a deep dive into that silent partnership that governs everything you see.